So we're going to talk about section 15.3 today. Conservative fields. And independence of path. So the first thing that I want to do is talk about imagine a scenario. So let's say we have either a charged particle or some kind of mass here. So this is either charged or mass, like a planet or something, and we're imagining the work done by the gravitational field or the electric field as we're moving some particle away from this mass. So we have some other particle, and let's say we start right at the other charge or right at the mass. So we know already, we've talked already that a field only does work. We're talking about a field that describes a force, only does work in the direction of motion. So let's say we move away from this charge or this mass a little bit. The field does work as we move directly away, correct? How much work is done if we move in a radial path? Like so. So we're moving along a circle here. Are we moving in the direction of the field? Does the field do any work at all there? No, because we're not moving. The force, the gravitational force or the electrical force always points directly towards the center. So we don't do any work if we go in that direction. So let me redraw that so it looks a little better. So now we're moving directly away from the center. We do a little more work. And I move this direction. Any work there?
Something that's actually straight along radius.
Right. So we're just going along a radius. I'm going to move this way. The field does a little work there. I'm going to move like so. No work. Move like so. Redraw that so we're going closer. Directly out from the center. Some more work along the circular path. No work. A little more work. No work. And then let's stop after this one. So this particle moves on this path where we go directly away from the center of the charge or the mass, and then along a circular path. Directly away from the center along the circular path. So the only portions where the field has done any work on the particle is when it's moving directly away. So the amount of work done doesn't depend on how far we move on these little paths that are on a piece of a circle. So if we were to calculate the work would only depend on how far we moved directly away from the charge or the mass. So I could go on any crazy, complicated path that we wanted. The field is only doing work in the direction of motion or opposite the direction of motion, depending on if it's a charge and what the charges are. So I could go on any kind of path. The work done by the field would only depend on where I started and where I ended. It wouldn't matter what I did in between, because the work's only in the direction of the charge or the mass. So would only depend on how far away, directly away from that charge or that mass I've moved. Well, it turns out that, well, gravity and electricity, the force due to gravity, force due to electrical field, is a conservative field. Turns out that for any conservative field, the line integral, we defined our line integral by talking about work. The line integral over a path depends only on the starting point and the end point. It doesn't matter what the path is in between. All that matters is where we start and where we end for any conservative field. And we said for conservative fields, our condition for conservative fields was that our field was the gradient of some scalar function. And we called f was the potential function. So if we have a conservative field, the line integral over some path in that conservative field only depends on the initial point and the end point. So that's going to be our big idea for today, and we'll talk about why this works mathematically rather than just conceptually in just a second. So we're going to start with what we're going to call our fundamental theorem of line integrals. So like we talked about in Calculus 1, I always tell the students when you call something a fundamental theorem, that means it's pretty important. So our fundamental theorem of line integrals. So we have some path. C is some path, and we're just going to state it in 2 dimensions. It extends to 3 dimensions very easily. So we have a parameterized curve, C, parameterized in terms of t, where a is less than or equal to t, less than or equal to b. And we have some open region R. So we're going to say if our field, if f is mi plus nj, so if our field is conservative, in our region, and we want our components to be continuous, then our line integral, the integral over our path of f dot dr, and I'm just going to rewrite this in terms of our scalar function, the gradient of the potential dot dr is f of x of a, x of b y of b minus f of x of a y of a. And what we're saying here is that our field f is the gradient of small f, and C is piecewise smooth. C has to be piecewise smooth. So this is our fundamental theorem of line integrals. If we have a conservative field, then the value of the line integral is just the potential function evaluated at A, our initial point, minus the potential function evaluated at, potential function evaluated at B, our final point, minus the potential function evaluated at A, our initial point. So this is just like we evaluate integrals in how we evaluated integrals in Calculus 1. We took the antiderivative, evaluated the antiderivative at one endpoint of our interval, subtracted it from the antiderivative at our other endpoint of our interval. So this is the exact same idea. If we have a conservative field, we can take the antiderivative essentially, which is our potential function, and evaluate that at the endpoints of the interval and subtract, and we have the value of that line integral. So this is it's a really powerful idea. If we know we have a conservative field, no matter what the path is, we can evaluate. There are things we can do that let us just figure out the value of this thing at the endpoints of our interval and evaluate it that way. So it simplifies our work in a lot of situations when we have a conservative field. So any questions on our fundamental theorem? All right, so we talked about this intuitively a little bit in terms of gravity and in terms of electrical fields. Let's talk about why this would work, why this fundamental theorem works. So we said F is conservative. Our field is conservative. So our field is the gradient of our potential function. And I'm going to write this in terms of its components. This is the partial of f with respect to x I hat plus a partial of f with respect to y times j hat. And our integral, our line integral of f dot dr, and we said we could evaluate that as f dot r prime dt is going to be the integral from a to b for a parameterized curve of df dx, dx dt. Dx dt is just the I component of r prime plus df dy times dy dt. That's just the y component of r prime times dt. Now if we look at this quantity by the chain rule, this quantity is just the derivative with respect to time of our scalar function. Just checking to make sure I have enough parentheses. dt. So this is the derivative with respect to time of f by the chain rule for multivariable functions. And when we take the integral of a derivative, we just end up with the original function, and we're evaluating this from a to b. So this equals f of x of b, y of b, minus f of x of a, y of a, by the fundamental theorem of calculus. So this dot product turns out to be the derivative with respect to time of our potential function, or derivative with respect to whatever our parameter is. So this is why this works. Basically, we're taking the integral of a derivative. Now, looking at this, what does this tell us if A equals B? If we go around a closed path? The work done is 0. If we start and end at the same place, these two quantities are going to be equal. So we end up with 0 work done, or our line integral evaluates to 0. So if A equals B, and that means we have a closed curve. The integral of f dot dr equals 0. So this is really nice because we could have some really complicated closed curve to evaluate a line integral over that curve, parameterize the curve, express our function in terms of parameter. It could be a lot of work. But if we know our field is conservative, that integral evaluates to 0. Now we can extend this argument to 3 dimensions. We would just add another component to our vectors. All the arguments would work out exactly the same. We would just add another component. So what we've shown here, what we've come up with, is that if f is conservative and continuous in some region, then the line integral of f along any curve from one fixed point to another is independent of the path we take between those points. So we call this independence of path. The line integral is independent of the path. So we're going to state that as a theorem. So everybody good with what we've done so far?
And you'll always be told if it's conservative. It's not like you have to figure out.
You might have to figure it out.
You do that in the
Right, and we'll talk about the test for conservative fields, a reminder about the test for conservative fields. So if you're given a problem of evaluating a line integral, that should be the first thing you think. Is the field conservative? Because that's going to simplify your work right away. Okay? So our theorem about independence of that path